Good morning, guys. Today we're doing 4.3, which is called L'Hopital's rule, right? This L hospital kind of thing. Uh, some French guy, I think. It's L'Hopital. All right. So this does make our lives a little bit easier. Um, and kind of before I get to that, let's just revisit some limits that we had. So if we look at this limit, I think this was unit one, and we said evaluate as x approaches 5. Well, we're going to get a 0 in the denominator, right? 5 minus 5 is 0. And whenever we have zeros on the bottom, bad things happen. So what we had to do is we had to kind of do a little bit of arithmetic and work our way around it. So sometimes we had to factor and cancel. Sometimes we just had to distribute and see what cancels. Sometimes we got lucky and we could just plug it straight in. But in this particular problem, we just had to factor at the top and then, see that that x minus 5 does cancel. And we're left with the limit as x approaches 5 of x plus 5. And now we can just plug it straight in. So we're going to get this equals 10, right? And then we had something like number 2 here, or the second one where we plug in infinities for everything. We're going to get kind of like an infinity over infinity. And the way to get around this one is we said, all right, just look for the biggest exponent. And I see an x cubed, right? So what I'm going to do is I'm going to divide every single term here by an x cubed. And we're allowed to do that. Just how we multiply the top and bottom by the same thing, we're allowed to divide the top and bottom by the same thing. All right, and when we do that, we kind of get a whole bunch of fractions inside of other fractions. And it really does look pretty ugly in the beginning, but it turns out to work quite nicely because we're kind of abusing the idea of infinity. Because when I plug infinity into all of these things, let's see what happens. This first term here, right? You have that x cubed in the denominator, so x cubed overtakes an x squared relatively quickly. If you wanted to simplify that, you just get 4 over x. But as we approach infinity, we get 4 over infinity, which is 0. So this whole term approaches 0 as x approaches infinity. Similarly, with the next one, that also approaches 0, and 12 over infinity cubed approaches 0 as well. Now, if you look at the bottom, the x cubes cancel, so you're just left with the 7 in that denominator, where all the other terms go to 0. Right? So we are left over with 0 over 7. Right? And 0 divided by 7 is 0. Right? So the limit of this function as x approaches infinity ended up being 0. We did have some shortcuts with that. We had this Bobo button thing. If you want to remember that, great. I guess it's an easy shortcut. But, do you actually understand what's going on when you use this acronym? Probably not. Right? So if you want to use that, great. But if we wanted to kind of express it algebraically, this is kind of what's going on behind the scenes here. All right. And then this very last one, we said 1 minus the cosine of theta divided by theta as theta approaches 0. We said that this one was just equal to 0. All right. So why is that? I told you guys, just take my word for it. All right. And then similarly, we had another trig function. We said the limit as x approaches 0 of sine of x all over x, we said this equals 0. Right? The source, see, that's even wrong. It was equal to 1. All right, so sine of x over x as x approaches 0 is 1. All right, and I just said, kind of trust me on that one. We'd prove it later. Well, today is that day. All right, before we prove those, let's talk about indeterminate forms. So an indeterminate form looks like this. Anytime we get something that's kind of undefined. So 0 divided by 0, what is that? I don't know. You type that in your calculator, it's going to say undefined. You ask Siri what that is, she's going to tell you something weird. Infinity divided by infinity. We have to be careful on that one. That is not equal to 1 because infinity is not a number. All right, it's kind of an idea. It's a concept. And it turns out, are different sizes of infinity. Like if you look at the set of natural numbers, 1, 2, 3, 4, all right? Those are, infinite, they go to infinity. But if you look at the real numbers, right, you have 1, 1.1, pi, e, all these just numbers, and they're negative 32, right? That is also, there's infinitely many of those, but there are more real numbers than there are natural numbers. And that's kind of weird to think about. All right, so both of those are undefined. Infinity minus infinity. Again, since there are different sizes of infinity, we don't know what the answer is for that one. Now, this next one, I don't like this one. It's kind of frustrating, but 0 times infinity, not 0. It's undefined. All right, 0 raised to the 0 power, also undefined. 1 raised to the infinity power, also 0, also undefined. And then infinity raised to the 0 power. These are all undefined terms, right? We can't get a solid answer for them. Now, some things that are determinate, infinity plus infinity, still equals infinity. Negative infinity minus infinity. If we were to do a little bit of algebra here, we get negative infinity plus infinity, which is still infinity. It's just going in the negative direction. 0 raised to the infinity power, that's 0, and 0 raised to the negative infinity power, also 0. All right, so these are determinant forms. So what we have to be on the lookout for is when we take our limits and we get 0 over 0 or infinity over infinity, that sort of thing, these indeterminate forms. If that happens, we can use L'Hopital's rule. All right, so L'Hopital's rule, it does make our lives a little bit easier. All right, so let's say we take a limit as x approaches c. C is just some number. Let's say we get a 0 on the top and we get a 0 on the bottom. All right, so let's look at like this guy right here. If we plugged in 5 here, you get 25 minus 25 is 0, and then 5 minus 5 also 0, right? So we got a 0 on top, 0 on bottom. What we do if we wanted to evaluate this limit, all we have to do is it's very straightforward. We have to take the limit as x approaches that same c value, but we're going to take the derivative of the top and we're going to divide it by the derivative of the bottom, right? So this is not the quotient rule, just straight up derivative of top, derivative of the bottom, right? And then we would plug in our value and see if we get an answer there, all right? So that is L'Hopital's rule. All right, so it's discovered by this guy named Bernoulli, but he's named after L'Hopital. All right, so let's just look at a few of these things. The limit as x approaches 0. Well, the first thing we need to do is we need to make sure it is, in fact, indeterminate. So I'm going to say, all right, e to the 3 times 0 minus 1 all over 0. All right, so this guy is e to the 0, and e to the 0, of course, is 1. So we're left with 1 minus 1 on top, which is, in fact, 0. So this equals 0 over 0, right? And that's bad. That's indeterminate. So we can use L'Hopital's rule. So I'm going to say this is equal to, and here's how I kind of notate it. I'm going to put an L with the apostrophe H, right? That is just kind of like a visual indicator that, hey, I'm using L'Hopital's rule. Right? So this is the limit as x approaches 0. Derivative of the top. What is the derivative of e to the 3x, right? Here's a good review on our derivatives. So that's 3 e to the 3x, and then the 1 goes away. All divided by 1, because the derivative of x is just 1. And, same kind of idea. Plug in 0 here. We're going to get 3e to the 3 times 0 all over 1, which, of course, e to the 0 is 1, so this equals 3. And so maybe let's confirm that. Let's just go to Desmos here and let's look at it. So let's just say like f of x equals, I think it was, we had e to the 3x and then minus 1, I believe, and then all over x. Right, so if I look at this function, oops, I gotta zoom out far enough. Here we go. All right, so if we look at this function, the limit as it approaches 0, keep in mind, we're not going to infinity, we're going to 0. Looks right here. And if you zoom in on 3, it'll say it's undefined. All right, so as x approaches 0, it's undefined. I'm sorry, f of 0 is undefined, but the limit as it approaches 0 approaches 3. Right? So there you go. This L'Hopital rule does in fact work. All right, we just have to have those indeterminate forms. Now, on the next one here, the first thing I notice is it's not like set up as a quotient. So here's what I'm going to do. I'm going to go ahead and rewrite this as a quotient. So I'm going to go ahead and say, all right, the limit as x approaches 0 from the right of x cubed over, I'm going to take that cotangent and I'm going to rewrite it as its reciprocal. I'm going to go ahead and call this the tangent of x. All right. So first things first, make sure it does in fact approach 0. So 0 cubed is 0. And then the tangent of 0 is also 0. Right. So we're going to get 0 over 0. So that is an indeterminate form. So when you're taking the AP test, these guys on the AP exam, those graders are kind of sticklers. They need you to confirm that it is in fact indeterminate before you take the derivatives or before you apply L'Hopital's rule here. All right, so this is the limit as x approaches 0 from the right of, well, what is the derivative of the top? The derivative of x cubed is 3x squared. The derivative of the bottom, what was the derivative of tangent? That was secant squared. We just had our test over this one, so hopefully you guys remember that. So let's go ahead and plug it in. So we have 3 times 0 squared all over the secant squared of 0. All right, so let's just go ahead and plug that in. Let's see what the secant squared of 0 is. I'm going to put SEC 0 and then squared. And that's going to pop out a 1. So this equals 0 over 1. And again, if you wanted to confirm it, go ahead and Desmos type in x cubed over the tangent of x. Let's see what we get. X cubed divided by the tangent of x. There it is. As x approaches 0, we're at 0. It's probably going to tell us it's undefined right here, right? But we're talking about as it approaches, not the actual value. So this is not a continuous function, but the limit does exist at 0. All right. Here, how about we do this? Let's go back to these two. So the limit, those first ones that we talked about, let's just go ahead and prove those two. So we said the limit as x approaches 0, I think we had cosine, was it cosine minus 1? 1 minus cosine. 1 minus the cosine of x all over, what's going on? All over x, all right? Now, if we look at this one, again, if we just plug in for 0, right, we're going to have 1 minus the cosine of 0 all over 0. Well, keep in mind the cosine of 0 is 1. And so we end up with 1 minus 1 over 0, which is in fact 0 over 0. So this is indeterminate. So using L'Hopital's rule again, I can say the limit as x approaches 0 of the derivative of the top derivative of 1 is 0 minus the derivative of cosine. What's the derivative of cosine? Derivative of cosine is negative sine of 0, or excuse me, of x, right, divided by the derivative of the bottom, which is 1. So let's go ahead and plug it in. So we have 0 plus the sine of 0 all over 1. All right. So this equals 0 over 1, which is in fact 0, right? Which agrees with our, claim from, way back in, I think that was like section 1.1. All right. So that one is true. Now, the last one, we said the limit as x approaches 0 of, I think it was the sine of x. Sine of x over x. This equals plugging in. We have sine of 0 over 0, which does in fact yield that 0 over 0, which is, indeterminate. So since it was indeterminate, let's go ahead and apply L'Hopital's rule again. So we're going to say the limit as x approaches 0, derivative of sine is cosine. So we're going to say the cosine of x over the derivative of x is 1. And then we evaluate this at 0. We're going to say, all right, the cosine of 0 minus all over 1 gives us 1 over 1, which is in fact 1, which again agrees with our claim from day 1. All right, so there you go. We have proved these two kind of identities here using L'Hopital's rule. All right, so I think there's that. So let's just try a couple more here. All right, so let's just look at this guy. All right, so we have x cubed over e to the x. So the limit as x approaches infinity, I think it was an infinity. Yeah. Of x cubed over e to the x. All right, so let's just take a look. Again, we need to confirm that it is indeterminate. So that gives us infinity cubed over e to the infinity, which is in fact indeterminate. So apply L'Hopital's rule. So I put my L apostrophe H just to let the reader know, hey, I'm using L'Hopital's rule. All right, so this equals the limit as x approaches infinity of the derivative of the top, that is 3x squared over, well, the derivative of e to the x is e to the x. All right, so if we plug in here, we have 3 times infinity squared over e to the infinity, which still gives us that indeterminate form. Right? Well, it's still indeterminate. So what are we going to have to do? We're going to have to apply L'Hopital's rule again, right? That's right. So you are allowed to use it multiple times. As long as you keep getting that infinity divided by infinity, just keep doing L'Hopital's rule until it simplifies down. Right? If you look at the top, look at those degrees. They keep moving down. So the next one is going to be 6x over e to the x. And you might be able to see where this is going, right? This is still 6 times infinity over e to the infinity, which still is that indeterminate form. All right, so if we do it one more time, this is going to be equal to the limit as x approaches infinity of, maybe we have 6 over e to the x, right? Derivative of 6x is x, which gives us 6 over e to the infinity, which is equal to 6 over infinity, which is equal to 0. All right, so all of that work to get this answer. So the limit here as x approaches infinity is equal to 0. And there we have it. I don't really want to do all that stuff over there. So maybe let's just do one of these. Now, if you look at these, you might not necessarily need to do L'Hopital's rule on them, right? So it says when possible. So you still need to double check to make sure that it applies, that you do have that indeterminate form. But some of these, they might factor and cancel. All right. If you like the old stuff, you can still do that. Like if you look at number 4, that's probably going to be a factor and cancel type of situation. So maybe you want to stick with that. All right. Um, but anytime we get these ones where we have the sines and the cosines in here, that might be the time to use L'Hopital's rule, right? Um, like if you look at number 6, they're just asking you to take the derivative. They're not asking you to take the limit. So let's see here. Let's do maybe we already did one with an e to the x. Let's do this one. All right, let's do the ones with some logs in here. So I'm just gonna screenshot this and then copy it to another page. All right. All right, let's take a look. We have the limit, natural log. We have x goes to infinity. First thing I'm going to do is don't forget those log properties here. All right, so if we don't do those log properties, I think we could still get an answer, but it's going to get really ugly. So let's keep in mind, I have that exponent of 2. So I'm just going to bring it down in front. All right, so I'm going to say the limit as x approaches infinity of 2 times the natural log of x all over. Similarly, I'm going to do the same thing here. 3 times the natural log of x plus 4. So if we plug that in, we're going to have 2 times the natural log of infinity over 3 times the natural log of infinity plus 4. Well, that's just infinity. Right? Can you cancel those? I don't want to say yes. All right, I'm hesitant to do that. Because again, different sizes of infinity. So I'm just going to say this is infinity over infinity. All right, so we can do L'Hopital's rule here. So I'm going to say, all right, according to L'Hopital, this is indeterminate. So I'm going to apply his rule. So the derivative of the top. All right, so remember, the derivative of the natural log is equal to 1 over x. Right, so the top on this one turns into 2 over x. Right, and then the derivative on the bottom here is going to be 3 over x plus 4 times the derivative of x plus 4. Well, that's just 1. All right, so let's take a look at this guy. I forgot to write my limit. So this is the limit as x approaches infinity still. All right, so let's clean this up. I have 2 over x times, I'm going to multiply the reciprocal, x plus 4 over 3. Right? And again, forgot my limit. So we're going to put a limit as x approaches infinity. This is equal to the limit as x approaches infinity of, let's see, the top turns into, that's a 2x plus 8. All over 3x. All right. So if we wanted to, I think I mentioned this. I think this was the second problem in this video. All right. I'm going to go ahead and divide everything by an x, right? Because that's the biggest kind of exponent here. So this is 2x over x plus 8 over x, all divided by 3x over x. And if you're going to notice, these x's cancel out. This term goes to 0 as x approaches infinity. These x's cancel out, so we are left over with 2/3. All right, so the limit on this guy is 2/3. All right, so on some of these, like I said, you don't need to use L'Hopital's rule, but it wouldn't be a bad idea. Anything that has a cosine or even a natural log or an e to the x, probably use L'Hopital's rule. Maybe on like 1, 2, and 4, those are just polynomials. See if you can factor and cancel some stuff out. But otherwise, there we go. That is L'Hopital's rule. Is there anything else on here that we need to mention? I don't think so. All right. But I think that was the last unit in this, or the last section in this unit. All right. So we'll see you guys later.